I left off with the last video, which is with question 5. We have scores on a college entrance exam. They're normally distributed with a mean of 1530 and a standard deviation of 320. And only those who score in the top 20% are accepted into some school or program or some such. So what is that minimum score necessary to be accepted? Excuse me. Well, this is going to be P sub 80, the 80th percentile, the score that separates the bottom 80% from the top 20. So we find a z-score that corresponds to an area of 0.8, because that'll be the area to the left of that, under the curve, to the left of that z-score. Then we convert that to an x value using this formula, x equals mu plus z times sigma. So the closest value to 0.8 on table A2, the standard normal, is 0.7995, and the z-score corresponding to that is 0.84. So here's the... okay, I thought I was going to have that thing. Right. Okay, so here's the standard normal, and when we go to the positive z-scores, we see that the area that is closest to 0.8 is right here, 0.7995, and the value just above it is too high above it, and the value below it is too far below it. And so 0.7995 is close enough for our purposes, so we use a z-score of 0.84. Okay? So the z-score is 0.84, so we insert these values into our formula, 1530 from the question, 1530, the mean, plus the z-score, 0.84, times the standard deviation, 320, and when we add all those up, we get 1,798.8, but we round up to 1,799 because the scores on the test are whole number values, or at least we assume they would be. Now part B is involves finding the probability that the mean of a sample is equal to or greater than or less than some value. So this is not a particular value, this is the mean of a sample. So so we use the formula for a z-score that we get from the central limit theorem from chapter 6, and that's the sample mean minus the population mean divided by this fraction, the standard deviation, population standard deviation divided by the square root of the sample size. So the sample mean in question is 1,750, so 1750 minus the population mean 1530 divided by population standard deviation 320, which is in turn divided by the square root of the sample size 71, gives us approximately 5.79. Now before we look at the implications of that, realize that, again, this numerator should have parentheses around it if you're doing this in the calculator, but so should the denominator. The denominator should have its own separate parentheses, or you might not get an accurate result. So this is the z-score that we get from these calculations, 5.79. It's very high. It's greater than 3.49, and if we look at our z-scores, we see at the bottom of the positive z-score page, it says for values of z above 3.49, use 0.9999 for the area under the curve to the left of the z-score. So that's the case here. The z-score is much higher than 3.49. So the area corresponding to this z-score is 0.9999. And so we subtract that from 1 and get a probability of 0.0001. because the question's asking for the probability that this sample mean is above 1750, greater than. And so greater than will be a very small area on the right. The probability we get from the z-scores is this area to the left, this very large area to the left. And so we can't even see this probability, but that's what we're looking for, is this area, this probability on this end. So we subtract a very large area to the left. Okay, now question 6 asks us to construct a confidence interval. And it says a confidence interval for the true proportion. Alright, so if we're constructing a confidence interval for the proportion, we're going to need the sample proportion. So we have a polling organization that takes a random sample of 248 people and finds that 165 agree with the current healthcare system. So what proportion is that? That sample proportion is 165 divided by 248, and that's approximately 0.665. We subtract that from 1 to get its complement. So P hat is 0.665, Q hat is 0.335. We'll need those for our formula for our margin of error. Because we are finding a confidence interval to estimate a proportion, then we'll use the standard normal. And because it asks for a 95% confidence interval, we know that the z-score that we use for a 95% confidence interval is 1.96. So we multiply 1.96 times the square root of P hat, 0.665, times Q hat, 0.335, divided by the sample size, 248. If we enter everything into our calculators correctly, we get a value of 0.059. That is our margin of error. So we want to subtract that from the sample proportion and add it to the sample proportion, and that will give us the low and high, the minimum and the maximum values of our confidence interval. And you can see those calculations here. 0.665 minus 0.059 and 0.665 plus 0.059. That gives us a confidence interval of 0.606 to 0.724. Now, based on this confidence interval, can we assume that the majority of people agree with the current healthcare system? So you have to be a little bit careful when you read the part B of each of these confidence interval questions. Well, the answer to this one is yes, because the majority means a proportion greater than 0.5. And the very smallest value in this confidence interval is well above that. So yes, we can be 95% confident that greater than 0.5, the majority, do agree with the current healthcare system. Now in question 7, it says in crash tests of 15 Honda Odyssey minivans, collision repair costs are found to have a distribution that's approximately normal, with a mean of 1,786 and a standard deviation of $937. We're asked to construct a 99% confidence interval estimate for the mean repair cost in all such vehicle collisions. Well, a 99% confidence interval means that the alpha is 0.01, and for that, because we're estimating a mean, we're going to use the t-distribution. So the t-distribution requires that we know our degrees of freedom. This is a test of 15 vans, so that's the sample size, 15. Degrees of freedom is then 14. And this alpha of 0.01 is going to be an area in two tails. So we find a critical value, a t critical value on our t-distribution that meets those criteria. So here we go. Here, let's go to the t-distribution. Alpha is the area in two tails is 0.01, and So we're going to look in this first column, and our degrees of freedom are 14. So we're using a critical value of 2.977. And there it is right there underneath the hand, 2.977. So our formula for the margin of error for estimating a population mean with our confidence interval is T sub alpha over 2 times standard deviation, sample standard deviation divided by the square root of the sample size. So that's 2.977 times 937 divided by the square root of 15. That gives us approximately $720.23 for a margin of error. We subtract that from the sample mean and add it to the sample mean to find the minimum and maximum values of the confidence interval. And you can see those calculations here, and we come up with $1,065.77 and $2,506.23. Now, based on this confidence interval, can we assume the average repair cost is less than $2,000? No, because the average repair cost could be anywhere from, well, it could be anywhere from $1,065 to $2,506, but it can be anywhere from $2,000.01 to $2,506.23, and that exceeds $2,000. Okay, so it is possible that our average repair cost could be a good deal higher than this $2,000. So the answer is no. You have to be careful about how Part B of each of these confidence interval questions is worded. Now in questions 8 and 9, we're asked to find the appropriate sample size for a particular confidence interval. The first one asks us to find with 99% degree of confidence the sample size needed to estimate the mean within 0.25 hours. Excuse me. So a 99% confidence interval means that we're going to use a z-score of 2.575. That's our critical value, 2.575. We're using z-scores and the standard normal because we are told the population standard deviation. When we have to be given the population standard deviation in this question, and so it is supplied. So the sample size needed is the critical value times the standard deviation, 2.575 times 1.87, divided by the margin of error. The margin of error is 0.25 hours, a quarter of an hour. That's what's meant by estimating within 0.25 hours. And then that value is squared, and that gives us 370.97. Now it doesn't matter whether this is 0.97 or 0.07 or 0.001. If it's anything above 0, we round up. Always round your sample size estimates up. So we round up to 371, and that's the appropriate sample size for to obtain this confidence interval. Now in number 9, we're again estimating sample size. In this case, we're estimating a proportion. So again, we're going to be able to use the standard normal and z-scores for our critical values. We're asked to find with 95% confidence a sample proportion within 2% of the population proportion. Within 2% means that our margin of error is 2%. 2% has to be in decimal form, so that's 0.02 in the formula. Well, a 95% confidence interval means that our critical value is 1.96. Our sample proportion is given here, 59%, which is in decimal form 0.59. Q hat, the complement of that is 1 minus 0.59, or 0.41. And our formula for estimating this sample size is the critical value squared times p hat, the sample proportion, times q hat, its complement, divided by that error squared. 1.96 squared times 0.59 times 0.41, and that's divided by 0.02 squared. If you enter all that in correctly, you'll come up with 2,323.21. Well, 0.2 is less than 0.5, but it doesn't matter. We still round up when we're estimating sample sizes. So our appropriate sample size is 2,324. And finally, number 10 asks us to create a 95% confidence interval estimate of the standard deviation. Well, if we're estimating the standard deviation, then we're going to use the chi-square. And the chi-square distribution has a couple of peculiarities, so I'll go through this a little methodically, perhaps, to make sure that we can follow along. So, since we are required to create a 95% confidence interval, the complement of 95%, which is 0.95 in decimal form, is an alpha of 0.05. That's the area in both tails of the distribution together, and so that means the area in the right tail, alpha over 2, is 0.025. We have 12, a sample size of 12, and so we use 11 degrees of freedom. And because our area in the right tail is 0.025, then we're going to use the 8th column in table A4. So there's the t-distribution. Here is the chi-square, which is table A4. And the area to the right of the right critical value is 0.025. So that's the column we're going to use. And we have 11 degrees of freedom. And so the critical value is 21.92 for this chi-squared sub r, the right critical value. Now, the area in the left tail of 0.025 means that the area to the right of that is 0.975, because 1 minus 0.025 is 0.975. So that's the area to the right of the left-tailed critical value. So let's take a look again at the chi-square. The area to the right of the left critical value is 0.975. So in this section we use the center column for the right tail, and we're going to use the center column for the left tail, and that's always going to be the case. Whichever one of these you use, the columns will mirror one another. So if we were using an area in the right tail of 0.01, then we would use an area in the left, to the right of the left critical value of 0.99. Anyway, in this case, the columns are 0.025, and the third column here is 0.975. And again, we have we have 11 degrees of freedom, and the area to the right of the left critical value, I know it's confusing, of 0.975 means that our critical value is 3.816. So, our chi-squared sub L, the left critical value is 3.816. Now we put these into our inequality somewhat backwards. The right critical value of 21.92 goes here in the left calculation, in the minimum value, and the left critical value of 3.816 goes into the right calculation, so it goes in the denominator here. 3.816, and we are not calculating a margin of error here. In this case, we are actually calculating the minimum and maximum values directly of our confidence interval. So the formula requires the degrees of freedom, which is 11, times the sample standard deviation squared. Well, we were told that the standard deviation was 31.7, and so that's here, and we square that. And we divide that by the right critical value, 21.92, and then take its square root. Over here, degrees of freedom, 11 times sample standard deviation squared, which is the variance, divided by the left critical value, 3.816, and then we take the square root of that. So if we enter all this into our calculators correctly, we'll come up with a minimum value of 22.456 and a maximum value of 53.821. The follow-up question, it's not labeled Part B, but the sort of Part B question here is, does the confidence interval contain the value of 35 millimeters, which is believed to be the standard deviation of sitting heights of all women? And yes, it does contain it. That's all we're being asked. Does it contain it? Yes, it is here between the minimum and the maximum value. Okay, so I think that takes care of us on a full review for the test. And I'll get these videos loaded up and see everybody Tuesday.